Welcome, welcome. Nice to see so many different people at the TU Wien again. I welcome you on behalf of our MBA, Space Architecture and Management, that is going on now. It's the second module, and I'm very glad that Advenit Makaya is again a lecturer in this MBA. And this lecture today is also part of the module Emerging Fields in Architecture. So we have some architects here, we have some engineers here, different kinds of people. Advenit Makaya is advanced manufacturing engineer at ESA, at the European Space Agency, in the ESTEC facility in Noordwijk. He describes himself that he supports the development of innovative technologies and new materials. I have to say that I know him as an expert. He never calls himself, but actually he is the expert when it comes to 3D manufacturing, out of Earth manufacturing, building on the moon, developing technologies for building, for constructing on the moon, in space, and even on Mars. And today we have something very new. Advenit Makaya will present an experiment, a successful experiment that has been conducted on orbit. And the main topic is metal 3D printing. Thank you very much for coming.
Thank you very much, Sandra. Can you hear me well? Okay, very good. Yes, thanks for the introduction. I think my definition of an expert is if you know more than the other person in the room. And I'm alone in my office, so I can call myself an expert, yes. So this presentation has been prepared or has received a contribution from many people from the entities you will see in the presentation, but I'd like to acknowledge my colleague Rob Postema, who is the program manager for the Metal 3D printer. Katerina is a research fellow and our colleague working on the material investigation on the printed specimen. And Anthony Lecossais from Airbus, who was leading the effort on the industrial side. So a few words about ESA. Maybe most of you know about it. For those who don't, we are the intergovernmental organization, 23 member states. Now Slovenia has joined us a few months ago. And our mandate is to support and provide Europe with the capability for exploration and use of space for exclusively peaceful purposes. So we have various sites across Europe. I'm located at ESTEC, the European Space Research and Technology Center in the Netherlands. And our headquarters are in Paris. We like to say that ESA costs every taxpayer in Europe not more than a cinema ticket per year. And with that, we try to provide access and possibility of use of space of European citizens. The different locations here, you have the European Astronaut Center in Cologne, the European Application Center on Telecom in Harwell, close to Oxford in the UK, ESOC, the Operations Center, so the Houston of Europe, in Darmstadt, and the ESTEC where I work in the Netherlands, among other things. So one particularity of what we do at ESA is that we are probably the only space agency that does the whole spectrum of space activities. NASA, for example, doesn't do Earth observation. JAXA in Japan is focused mainly on exploration. But we really do the whole thing, science, so mission to other planets, astronomy, etc. Human and robotic exploration on the moon, Mars, and low Earth orbit. We do Earth observation, so climate change mitigation and measurement as well. More measurement than mitigation, actually. What we call connectivity and secure communication is the telecom satellites. And navigation is Galileo, basically, the project from the European Union, for which ESA is the technical arm, the executive arm, which provides satellite navigation capabilities all over the world, and in particular in Europe. And we have enabling functions. One of them is technology. That's where I'm from, where we promote the development of future technology for future space applications. Space transportation is the launchers, the rockets, and the operations is the, yes, you think about Houston in the movies. It's basically operating the satellites once they are in space. We have been celebrating the 50 years of ESA this year. And I'm going to play a little video which shows what ESA has done for European citizens over the past 50 years. So you have a nice brochure you can find online. It's publicly available, which describes some of those achievements. And I think it's number 36 in this video is the topic of today's lecture about making the first metal 3D printed part in space. So that's the topic I will dive in now. First, let's ask ourselves why we would try to manufacture things in space. So if we look at exploration, the way we do exploration now, human exploration in particular, is that we are relying a lot on supplies, resupplies from Earth. And we have to have redundancy, which means we have to have 2, 3, 4, 5 of each, just in case something happens. You may have heard a couple of years ago about those 2 US astronauts who went to test the Starliner vehicle to resupply the space stations. They went for a week, and they ended up spending 9 months in space because the Starliner had a problem, and they didn't have any vehicle to pick them up until 9 months. So when something like that happens, we need to be able to have enough supplies for them to live and survive in space. So a lot of redundancy. And actually, there has been a study by MIT a few years ago showing that probably 80% of the supplies will never be used. They are there either on ground or on the ISS just in case something happens. So that's a lot of waste, but that's needed by the requirements of a safe human crewed mission. So if you introduce the possibility to manufacture things directly in space, then you decrease the need for resupplies from Earth, and you decrease the logistic effort to have to resupply things from Earth. If on top of that you introduce the possibility to recycle what you have manufactured, then you decrease even more the need to bring things from Earth to space. So this was the topic of a study by the MIT in 2016, which showed that you could theoretically decrease by up to 98% the amount of supplies the amount of resupplies that you would need from Earth to maintain a crewed space mission. So that's one advantage of manufacturing things in space. Now, if you think a little bit bigger than just a crewed space environment, the way we do space missions at the moment is we design a spacecraft on Earth, we put it in a rocket fairing, and we launch it to space. There is an inherent limitation to that, is the size of the rocket. And the size of the rocket for some of the aspects of the space mission determine the performance. If you think about solar arrays, for example, the size determines how much power you can give to your satellite and how many things you can do with your satellite because of the payloads that need energy on the satellite. Same thing for antennas. For some applications, the size of the reflector antenna determines what we call the throughput, so the flux of data that you can transfer with your antenna. So if you introduce the possibility to manufacture things directly in space, then you free yourself from the limits of the launcher fairing. So you can make bigger solar arrays, which means that for the same size of the satellite platform, you can put more payloads and you can do more with the same launch. There are some applications in Earth observation, for example, which we call a satellite train, where you have 3, 4 satellites in a row, which do different types of observations, and then you combine them for your mission. if you are able to have larger solar arrays, with the same platform, you can put more instruments and you don't need to launch 3 or 4 satellites. So with one launch, with the cost of one launch, you can do what you would need to do with 3 or 4 launches. So cost reduction for the Earth observation mission or the other type of mission, decrease of the number of launch, which have a knock-on effect on the sustainability of the mission, the impact on the atmosphere, etc. So clear benefits there. We talked about antenna, same thing, larger antenna, higher data throughput for the same type of satellite, the same cost of launch. And the data throughput for telecom operators directly translate into business benefits, which ultimately is the driver for telecommunication missions. Science is the same. Larger telescopes means larger aperture and more science return for your mission. The largest human-made telescope we have at the moment is the James Webb that we probably saw. And I don't have a picture in this presentation, but James Webb reaches about the limit of what you can put in the current rocket fairings. And on top of that, it had complex mechanisms which took several weeks to deploy in space. So there, if you manufacture directly in space, you are free from these complex mechanisms and free from the limitation of the fairing. Another aspect of launching, of bypassing the launch and making things directly in space is that the launch phase is the most demanding part of the lifetime of a satellite from a mechanical point of view. It lasts a few minutes, but that drives the requirement for the mechanical definition, the mechanical design of your satellite. Or in simple terms, you need to beef up the structure of your satellite just to resist the launch, because once it's in space, it's sitting nicely in microgravity, and it doesn't need to be that strong. So you can decrease the amount of material, decrease the structural requirements if you are able to assemble or build directly your spacecraft in space. Then if we think in longer term, if you're able to manufacture in space, then you're also able to repair in space, and you're also able to recycle in space. And thinking even farther, you can use space debris as a source of material. So space debris doesn't become a problem anymore, it becomes a resource, so it becomes part of the solution. And then it opens up possibilities like space-based solar power, for example, which requires very large structures, or even further, the very large-scale habitation in space, the O'Neill ring and things like that. So really, it's a game changer to be able to manufacture things in space. Closer to the topic of space architecture, infrastructure on the moon, on Mars, on a terrestrial body could also be manufactured from local resources, where you would not have to bring all the structural materials to shield your lunar base, Martian base, etc. from Earth. Significant simplification of the logistics of the mission, significant reduction of the cost of the mission. And then there's a third area which highlights the benefits of manufacturing in space, is to use the unique space environment to do things that you could not manufacture with the same quality on Earth. You have a picture here of optical fiber. That's probably the most researched use case at the moment for manufacturing in space to bring back on Earth, because making optical fibers in space means that you have less impact of disturbances on the solidification of the crystallization of the fiber, means less defect, and a fiber that conducts light and information faster. We are talking about milliseconds faster. It doesn't matter too much for us. It matters a lot for financial people, because that makes a difference between this trader and the next one. So, and the optical fiber is just an example, semiconductors for faster computers, etc. So really, manufacturing in space is an area that's definitely worth a look, because it can unlock a lot of benefits for space missions. Of course, to realize that dream, that vision, you need to develop capabilities which we don't necessarily have at the moment. The first one is to develop manufacturing processes which work in the space environment. Space is hard. There's no air, there's no atmosphere, there's no magnetic field or atmosphere to shield you from radiation. Temperatures can vary very widely, whether you are facing or away from the sun. And the manufacturing processes have to be able to operate in those environments. The second thing is, if you manufacture in space, you don't have a laboratory, you don't have a team of technicians to check that what you manufacture is good, is the right quality. So you need to develop the processes to either monitor the manufacturing process or verify the parts that has been manufactured to make sure that it's fit for purpose. And then you have auxiliary capabilities such as definition of how your factory would look like. If you're building large structures, how will you control them in space? How you will handle the end of life? So a lot of different capabilities that are needed, which are not there at the moment. And focusing on the first one, developing the manufacturing processes which actually operate in space, is one of the drivers behind the metal 3D printing experiment that we did. Now we have seen why we would manufacture in space, what is needed to do it. Now let's focus on what we are able to do already in this field. So 3D printing, additive manufacturing of polymers in space, it has already been demonstrated more than once. So the first polymer 3D printer by NASA was launched and operated in 2014 with the company that was called Made in Space at the time, which is now Redwire. And it printed some parts on the ISS showing that plastic can be printed in sustained microgravity in a crewed environment. This was a simple plastic, your toy plastic, not very strong ABS, but it showed that it could be done. Then 2 years later in 2016, NASA, again with Made in Space, launched and operated what we call the Additive Manufacturing Facility, which is still on the ISS. It's meant to be a commercial permanent facility, means anyone, any company can pay Redwire to produce things in space. I think in reality it's mainly NASA being the customer, but in theory it's a commercial facility. So the difference with the first printer is that it could print what we call engineering polymers, so stronger polymers, which can actually have structural uses. Which can be used for making real-life parts in space. Then 2 years later, in 2018, NASA launched a refabricator, which could not only print, but also recycle in space. So introducing, again, the benefit of recycling what you make. The refabricator actually could not work to the extent that they wanted, so NASA decommissioned it in 2021. But nevertheless, this was an attempt at developing recycling capability in space. And what about Europe, you will ask me? So Europe, the Italian Space Agency launched the POP 3D printer in 2016, so which basically did what the NASA printer from 2014 was doing. So it did a one-off printing of polymers, so not high-quality polymer, but it showed that Europe can also additively manufacture polymers in space. Now, if we move to composites, so the carbon fiber reinforced composite. So the first and only demonstration so far was by China, the China Academy of Space Technology in May 2020, where they demonstrated, it's not clear if it was pressurized environment or unpressurized, but it was during the testing of new crew spacecraft where they demonstrated that composites can actually be printed in sustained microgravity on Earth's orbit. And so far, no other entity has printed composites in space. Now moving on to metal. So the German Space Agency, DLR, worked together with the Federal Materials Research Institute called BAM to develop a metal 3D printer. So it used powder. It's a powder bed laser powder bed fusion process. So I would say the metal 3D printing parts on Earth are mainly made with this process using powder and the laser which scans the bed of powder, because it provides a combination of good mechanical properties and also part accuracy. Now, what's the problem with working with powders in space?
They don't stay together.
Yes, the microgravity, your powder will go all over the place. So you will have to think about ways to keep the powder together. They found a very clever way of doing it, is that they had a kind of vacuum cleaner which was sucking below the powder bed, so the powder bed stayed together, independent of the gravity level around it. So it worked very well. They did it in a parabolic flight in 2018, printing stainless steel. And they did it in a suborbital flight, in a sounding rocket flight in 2021, printing zirconium-based metallic glass. What would be the problem of this approach with the suction of the bed?
You need a filter small enough to filter out the air, but not too big to suck in particles.
Yep, the size of the filter. What other limitation do you see? You need a gas, which needs to be I would say recycled if you want it to be sustainable. Another limitation is that you are limited in the thickness of the bed. If you have too thick a powder bed, then your suction cannot work very well. You have a variable effect of your suction as the powder bed is increasing or decreasing. So you can only make relatively thin parts. Nevertheless, that was the first time that metals was 3D printed in space, but not on orbit. It was a sounding rocket, it was a suborbital flight. You get about 6 minutes of microgravity. So until 2014, until 2024, until we launched the metal 3D printer, there had been no metal additive manufacturing on Earth orbit in sustained microgravity. So that set the challenge for us. So the objective of the technology demonstrator that we designed, the metal 3D printer, was to develop an additive manufacturing machine which can basically demonstrate 3D printing on Earth orbit in sustained microgravity and make actual specimens. So we wanted to understand the limitation of such a machine in terms of part quality, specimen accuracy, etc. And we also wanted to test the capability to make actual functional parts for astronauts in a future mission. And we wanted also to understand how it would work out from an operation point of view, involving the crew, involving people on ground, to actually print metallic parts during a crewed space mission. So the development and the installation of the metal 3D printer was also part of the Hugin mission from the Danish ESA astronaut Andreas Mogensen, who was on his second mission at the time of the printer was launched. So the team behind the printer development, so this project was a co-funded project between ESA and Airbus Defence and Space, mainly the team in Toulouse. And so Airbus was leading the industrial team, and they were helped by Additive, which is a small French company which makes 3D printers. Cranfield University in the UK, which has the expertise on the additive manufacturing process. We'll see more about the process in the next slide. And Hive Tech Engineering is a small Italian company that has experience in making payloads for the ISS. So you have a good combination of experience between a very experienced large system integrator for spacecraft, a company who knows about the process a university who knows about the theory of the process, and a company which is used to making payloads. Now, if we look a little bit more closely about the process we selected, so we decided not to work with powder for the reason we have talked about before. So we selected a wire-based process. With wire, you don't have a problem with reduced gravity. And we selected the direct energy deposition process. So the way it works is that you have a laser which basically shines on a substrate, a metallic plate, and creates a hot zone. And you put a metallic wire into this hot zone, so it creates a melt pool, a pool of liquid metal. And then you can scan the surface to draw a 2D pattern. And if you repeat it layer by layer, you get your 3D printing part. So the different physical phenomenon that you have is radiation. You are losing heat to the environment around the melt pool. Conduction, because heat is flowing through the build plate, and also if you are 3D printing your part through the part itself. And convection, because the air or the gas around the melt pool is mixing itself due to the difference in temperature in the different parts of the build chamber. And you have a certain number of, physical phenomenon. You have the surface tension, which determines the shape of your melt pool. And it's quite important because the shape will determine as well the quality of the layers. You have buoyancy. You have recoil, is the effect of the laser on the melt pool itself. And vaporization, because you are working at quite a high temperature. So the difference with working with polymers, most of the first demonstrations of additive manufacturing in space were polymer. Difference with metal is that you have higher temperature. You have vaporization of gases, etc., which you need to handle potential spatters of metal, which you need to handle in a crewed environment with astronauts. So that derives all sorts of safety requirements. And then you have a certain number of process parameters you need to play with to ensure that the quality of the part is good. Is the laser spot size, the laser power, the inclination of the wire as well affects the quality of the print, the speed, and the type of gas that you use. To monitor that, we had a set of sensors, basically consisting of a camera and a system to measure the height of the printed layer. So to summarize a little bit, what we wanted to do is to print parts, or to demonstrate that you can print parts on the ISS, and then compare with parts printed on Earth. So you see the differences. 1G gravity against microgravity. If you are in microgravity, you don't have the effect of convection, so that affects your thermal behavior of your part. And we try to maintain a similar gas environment around the printed parts, both on ground and on the ISS. We have looked at the process. Let's look a little bit more closely on the machine. So as we said, laser wire direct energy deposition is the process. We decided to work with stainless steel. Stainless steel is your kitchen sink material, to make it simple. Any idea why we use stainless steel? If you think about 3D printing of metals for space hardware, you usually work with titanium, you usually work with aluminum, which are light and strong. Why did we pick such a casual material like stainless steel? Oxidation, you are on the right track, yes, but titanium and aluminum oxidize as well. So why didn't we go for the fancy aerospace alloys? Cost is one thing, but since it's a technology demonstrator, small parts, it was not going to affect a lot. We are not making big things. Sorry? Softer, that was not the reason.
To which change volume with temperature?
The thermal expansion that was not the reason as well. It's not very different from aluminum. The reason is we talked about oxidation. What do you need to do to protect hot metal against oxidation when you print? It's the atmosphere. You need to have what we call a shrouding gas, which prevents oxygen from getting close to your molten metal. If you work with aluminum or titanium in particular, what sort of shrouding gas do you use? Do you know? Argon, exactly. Argon is a no-go in a crude space environment because argon is heavier than air. If there is a leakage, it takes the place of air and people die. We don't want that. There's a gas that is actually the most abundant gas in air, which is allowed on the ISS. Which one is it? Nitrogen. The problem with nitrogen and titanium is that they form nitrides, which are hard, brittle particles, and you absolutely don't want that in your printed material. And what alloy family, metallic alloy family, is very good friend with nitrogen? Stainless steel. It actually makes stainless steel stronger, nitrogen. So that's the reason why we selected stainless steel. The wire diameter is 600 micron, 0.6 millimeter. Laser output power 300 watt. It's also dictated by the safety requirements on the ISS. It's quite a small build volume, 8 centimeter high by 5 centimeter diameter, but it's good enough for the demonstration that we wanted to do. Typical printed part is 80 to 200 grams. And the wire feeder, we have the cassette with the wire feeder, contains 1,000 grams of stainless steel. What was driving the maximum mass in our cassette was actually the filter. As we said, with metals you have high temperature, evaporation, spatters, and you have a filter which collects all that so that it doesn't end up in the cabin of the ISS. And this filter gets clogged after about 1 kilogram of burning metal. So that drove the amount of material we had in the cassette. Looking at the printer itself, we had a seal box to protect the crew around it from temperatures, fumes, etc. We work with a very small content of hydrogen or oxygen in the atmosphere for the reason we talked about, the oxidation. And what we did is we purged the chamber with nitrogen to decrease the amount of oxygen, so below 0.5%. The pressure was quite low, 0.88 bar. And we had actually a fixed laser and a moving substrate with a 4D motion table, so 3-dimensional displacement plus 1 rotation. We had an electronic box with the control, and the printer was placed in the EDR2, the European Drawer Rack Mark II, which was a new rack on the ISS. So on top of having a new payload, we also had a new rack, so that took a little bit longer in commissioning the whole system. What we wanted is to minimize as much as possible the work that the crew has to do, because the astronauts are very expensive and they have better things to do than pressing the buttons on the printer. So all the printing was operating from ground. The crew only had to install the printer, open it and remove the parts when it's finished and put in the new substrate. Plus occasionally if something goes wrong they have to tinker a little bit with the printer, but nominally that's all they had to do. And on the ground, we had the user operation center called CADMOS in France, supported by Airbus, who was actually doing all the printing. And the way it was done is a technology demonstrator. It was not by any means meant to be a fully automated printer. So it was really a manual operation. Layer by layer, the operators on ground were checking the parameters, using the data from the sensor, and doing what we call baby steps. So if a layer looks strange, they change the parameter to make sure the second layer is better. So the printing took a long time because of these baby steps. And as you said, we had, a camera, profilometric data to see the profile of the printed layer and the temperature and oxygen level sensor. Now let's look at what we plan to print. We had 4 specimens nominally to be printed. This is the first one. It consists of 3 tensile strength specimens and 3 bending strength specimens. So the idea was to print this on the ISS, print the same thing on the ground using the same printer, and then do some mechanical testing and material investigation to see if there is really a difference between the metal printed in space and on Earth. Second specimen was this one. It consists of 3 concentric cylinders. The reason was to challenge the printer a little bit in making thin layers or thin walls, and to see whether the walls would be of better quality on Earth or in space. And the outer layer has an overhang to see how far you could push the printer in making a horizontal shape. Third specimen is meant to replicate what we call a compliance mechanism. A compliance mechanism is a mechanism which doesn't have any screws. Of course, the resolution of the laser direct energy deposition process is quite poor, so it's not a finished mechanism, but that was the idea, to make to push towards printing a part that would be used in a crewed and mission scenario, etc. And the 4th specimen was designed by the Technical University of Denmark. As I said, the installation of the printer was part of the mission of the Danish astronauts, so they proposed this, which is a mirror holder. You can imagine that you put a mirror here, and then you, by hitting it, you can see the thermal expansion of the different arms to see if the mirror would stay leveled up or not, and seeing whether printing in space or on Earth affects this thermal expansion behavior. As we said, we plan to print 1 example on the ISS, 1 example on Earth, and do a certain number of material investigation, which you see here. Non-destructive inspection to see the internal microstructure, mechanical testing, microscopy, etc., to compare the properties of the sample printed on Earth and in space. Mission timeline. So we started this project in 2017. The design of the printer itself ran from 2019 to 2020. We built what we call the engineering model. It was finished in September 2020, which allowed to do some preliminary tests. And the manufacturing, assembly, integration, and testing of the flight model was completed in 2023, and we launched on the 3rd of January 2024 on a resupply mission to the ISS. Andreas Mogensen installed the printer in February 2024. It's very big, but it's microgravity, so it looks easy. And in May 2024, we did what we call the commissioning. So basically, we print lines and we print an S to check that all the parameters of the printer are correct. Between May and August 2024, we printed the first part, those 3 tensile, 3 bending parts, and the whole printing took 25 days. As I said, it's baby steps. So every layer, the user operation center people on the ground were checking the parameters and changing them. And also, it's a technology demonstrator, so it was not meant to be automated once again. And another reason why the printing took so long is that we could only print maximum 4 hours a day. Do you know why?
I saw in the slide that there was some noise.
Yes. So it's acoustic reason. So the printer is noisy, and there are regulations on the ISS not to expose the astronauts to too much noise. So we were limited to 4 hours a day, and that part took 25 days. Fair enough. So on the 21st of August 2024, 2 US astronauts, there was no European astronaut on the ISS at that time. So Janet Epps and Sunita Williams opened the printer and took out the first part. And by the way, Sunita Williams is one of the 2 astronauts which got stuck for 9 months on the ISS, so we found something interesting for her to do. So in August 2024, that was the big achievement. We achieved the very first metallic part fabricated on orbit, on Earth's orbit in sustained microgravity. So big European achievement. As we saw, the first polymer parts were American, the first composite part was Chinese. First metallic part printed on the ISS is European. So we can do things when we put the will and the resources behind it. The other specimen, so specimen B, the thin-walled structure, has been printed as well. It's currently sitting on my office in the Netherlands for material investigation. Specimen D, the Danish specimen, is at the Danish Technological University for material investigation as well. Unfortunately, specimen C, we had to stop it. There were some glitches on the printing, probably because of the thermal interactions between the different arms of the mechanism. And we decided to stop it and to try to resume it later if we get the time. The material investigation is ongoing. This is my colleague Katerina, who is doing some microscopy investigation. It takes longer than expected because we have to do it along with our other tasks, but we can start to see results already. The mechanical properties are well in line with what you find in the literature for 316 stainless steel printed with this process, the direct energy deposition. And the porosity starts to tell us interesting things about the strategy we adopted for the printing. But all that will be published in a report, which we hope early next year. In an article, sorry. The lessons we learned from this experiment, so the ratio of the volume and the mass of the printer with respect to the printable volume are quite important. You want to maximize as possible the printable volume. There's still, although we wanted to minimize the time involvement of the crew, there's still quite a lot of time required for the crew for installation, reinstallation of the specimen, etc. This is something we need to work in the future. Safety requirements are always very important. We didn't have any problem here, but that's quite important if we move on to higher temperature metals, etc. And the fine-tuning the printing process is challenging. This baby step approach, which was fine for a technology demonstrator, is clearly not sustainable for a long-term printer. And of course, with this direct energy deposition process, you get a very rough, very coarse structure, which needs machining, post-machining. So either we develop that capability or we move towards processes which give a better resolution for the printed part. You see here the funny shape of the wire. So things happen, wires get stuck, they get bent, and we need to have some sort of monitoring and correction process for when it happens, minimizing the involvement of the crew to repair it. So that highlights areas for improvement: accuracy of the printed part, more complexity of the printed part, quality assessment of the part, smoothness of the printed surfaces, etc. Automation to avoid this baby step approach, including using modeling, simulation. If you're able to simulate, then you need to do less monitoring and test, and ultimately digital twinning of putting in parameters and knowing more or less exactly what will come out of it. Miniaturize the printer or maximize the print volume. And reducing the resources in terms of energy, crew time, etc. Next steps to finish the material investigation. As I said, hopefully early next year we produce the paper. And we managed to get a bit of money for a 5th specimen. We are working with the DLR to print a thruster It's actually a rocket nozzle thruster that they had worked with on another project, and they are going to try to print it with this metal 3D printer. We are preparing a topical team, so it's basically a university team of academics who will think about how metal additive manufacturing can serve science in space. It's in the pipe. Basically, metal 3D printing in space is part of a bigger picture. We saw it in the first slides of developing manufacturing capability in space. It's an initiative which we call Out of Earth Manufacturing, and we have just issued a white paper, which is available online at the link here, and which I recommend to get a little bit of an understanding of the state of the art in this topic. On that, I stop boring you, and I answer any question you may have. Thank you. Yes.
Mike?
We have.
So instead of doing the powder approach, just basically we're soldering in space.
Yeah, you can think about it as a layer by layer welding, yes.
Okay.
We had one here.
Can we use the mic? Because the further recording,
Hi.
otherwise it's not recorded.
Thank you very much. It was very interesting. I have a question about one of the goals that you stated at the beginning was that one of the motivations for having printing or manufacturing in a space was to recycle the debris that already existed. But it seemed to me that the way that you went about this printing had a fundamental shortcoming. Was it that the debris or the recycling is not as big of a goal as it seemed to me at the beginning of the talk? Or the plan is to have manufacturing that doesn't have human crew, so the not use of oxygen wouldn't be as important?
So before you run, you have to learn to walk. So the recycling is definitely part of the picture because that's what drives the sustainability. But this is a technology demonstrator. What we wanted to do is to show that we can print a part. So the recycling was definitely not in the picture here, but that remains a goal. To develop recycling capability, you need to develop the possibility to take the part, put it in a shape that can feed the printer, whether it's powder, whether it's a wire. And these are technological building blocks which we have not yet started to work on. But yes, as I said, before you run, you have to start to walk. And this is us taking the first step.
Thanks. May I ask a question? Yeah. Thanks. Congratulations on your achievement again. I have a question regarding the precision you're printing. So as we saw, the first printer has a little coarse. However, it's a great achievement. I would imagine in an aerospace manufacturer, you would ask for a lot of precision. And I would want to ask, how far are we from the precision we would actually require to fix the spaceship? And what is the main roadblocker there? Thanks.
So yes, we are not at the precision we would like to have for an actual part. And the parts, for example, these tensile and bending specimens here, we machine them on ground. We machine them in our workshop to be able to test them. So this was a process choice, which used a wire, knowing that it's not a process that produces a ready-made part. So the reason, the way you solve that is to develop in-space post-processing capability, machining. For example, NASA has started to work on on-orbit machining. The second way is to choose a printing process that gives you already usable parts. And the process that DLR developed with the powder gets you closer to that. You see the quality of the printed range. With the powder, you get much better accuracy. So yes, we know the accuracy is not there. You're perfectly right, it's not good enough to put in the vision of repairing things in space or making spare parts in space. But yeah, now we are at a crossroad. Either we focus on developing post-processing machining capability, or we diverge to another printing process which gives us a better quality.
Hi, here. I have a question connecting to the last one a little bit. So let's say one of these objects is placed in a vacuum environment. So a common problem of materials is off-gassing. And so the molecules inside, so the trace molecules, destroy the structural integrity. What measures could be made or methods additionally to ensure structural integrity of a 3D printed object placed in a vacuum?
Yeah. So that's one of the drivers behind the move from this printer to this printer, is that the first family of plastics that they used here and that we used in Europe, they outgas a lot. These are cheap polymers, low temperature, ready to print, easy to print. But if you want to really make parts that are used in space, you move to low outgassing polymers, and also which have better mechanical properties. And there you are talking about engineering polymers like high-density polyethylene, PEI, etc. So the main solution to outgassing is to choose a material which doesn't outgas, which can make your process a little bit complex. We don't have this problem with metal because metals do not outgas in vacuum. That's also a good incentive in developing metal additive manufacturing capability.
Okay. Thank you very much again for the great talk, and congratulations for the achievement. I don't have much knowledge about metal 3D printing, so my question might be a little bit off, but I appreciate a response. So the first set of questions is, why do we need the nitrogen? Why not vacuum? Is it just for convenience or for the convection, for heating? And if convection is the issue, do you only have heating components for the printing, or you have some heating plus cooling mechanism to replace the convection?
Why do we use a shrouding gas and not vacuum? Because vacuum is free in space, but it's not free on the ISS. You have to create the vacuum. So it's less of an effort to have a gas and decrease the pressure than to try to create a vacuum that is good enough to print. That's the reason why we went for a shrouding gas. Nitrogen is cheap, is abundant, so that makes it easier. Convection, yeah, let's say on Earth, we would have convection. If you start to move to vacuum, of course, some additive manufacturing processes need vacuum, like electron beam, for example. But for this sort of thing, we are used to working with convection. So if you move to vacuum, there's more of a learning curve to understand what it would do to the metal. So rather than moving to vacuum and the absence of convection, we work with something we know, which is a low pressure gas and convection.
I'm here. I have a question that sort of links into that with the shrouding gas. You said that argon is a no-go on the ISS because of its high density and it accumulates. Could you elaborate on that in the context of microgravity?
Of microgravity? Well, yes, you're right. In microgravity, you don't have this effect of argon replacing the air because it's heavier. But you do have the effect of argon choking people if it's still in the air. So that microgravity doesn't change anything there. It's just that it would not behave the same filling the room, but you don't want it near the astronauts.
So, this is me now. What other technologies of additive manufacturing did you consider to use before you went with VAM? because I think there are other technologies, let's say powder bed or binder jetting, which might be of something.
Yeah. So we had a trade-off of which additive manufacturing process to select. Powder was low in the trade-off because of the difficulty in handling powder in reduced gravity. Even if you use binder jet or blown powder, you still have powder. And binder jetting, you have a consumable, which is the binder, which for sustainability reasons is not good in the trade-off as well, because you would have to replenish or recycle the consumable. So we ended up on wire processes, WAM and laser direct energy deposition. And we went for laser. I was not in the project at the time of the trade-off, but I suspect it's for power reasons that they preferred laser over wire arc.
Thanks again for your presentation. I would have a follow-up question. So you said that you still have to decide which direction to take with this, either improve this technology or develop a new one. And I was curious about what do you think would be more feasible in the future? What's more likely to happen?
So if you ask me, I would say both. I don't think we need to restrict ourselves in choosing one method or the other. I think we should push several methods, and then we see which one applies to what use case. Some processes are good for very big parts, which doesn't need a lot of accuracy, and some are good for tiny parts with a lot of accuracy, like on Earth. Unfortunately, it's money-driven, it's funding-driven, so we don't have the funding at the moment for a second printer. What we have the funding for is for a study which would look at the lessons learned and make some recommendation to define another printer. So I don't know where the study is going to go. It hasn't started yet. But I really hope that somehow we get enough funding to pursue different directions.
I noticed there were no interface mechanisms or layers on the print. How do you get them off without a wire EDM machine?
Who is speaking? Sorry, I can't see. Ah, yes, okay, sorry. Once again, please.
I noticed there are no interface mechanisms on the printed parts. How do you get them off the build plate without some sort of wire EDM machine of that sort? Because it's pretty much impossible, I guess, or for me at least, to get them off without one.
Yeah, no, very good question. Same for as the post-processing and the machining. We did it on Earth. We did it on Earth in a workshop, but it's not going to work in a space mission scenario. So the same as the post-processing, the machining, we'll have to find a way to have build plate detachment of the part, automated, robotically made, etc. We cannot ask the astronauts to have a sew. So there are different strategies to do that, which we have started to explore in another activity. One of them is to print very thin struts as the first few layers to make it easier to detach. There was a very creative one from Airbus which looked at changing the composition of the metal in the first layers to create what we call intermetallics. Intermetallics are mixtures of metals which are hard and brittle. Hard is not good, but brittle is good because you can snap it easily. But that adds complexity because you need to change the composition of the metal as you print. So yes, detaching the part from the build plate is a very important challenge. We haven't found a solution yet, but that's part of the technology roadmap.
Yes, especially on those pull rods. Do you have an expected loss of tensile strength? And how much would it be? Like you mentioned, the tests are still ongoing.
What do you think?
I think there would be a loss.
Okay. was, my opinion was that there would not be a lot of difference between specimens printed on Earth and in space, because this process is mainly surface tension driven. The melt pool is not very big, so it's not so much affected by gravity. It's more the surface tension between the liquid and the solid at this very small size of melt pool, and surface tension is not affected by gravity. So my gut feeling was that there would not be a lot of difference. We are still doing the tests, but I can tell you there's not a lot of difference.
Concerning the resolution of the parts, you took with 0.6 millimeter wire. Why didn't you choose thinner wire? Is it too hard to handle?
Yes, yeah, that's the reason. It's too hard to handle. You saw the picture of the wire which went like this. It happens a lot more if you have a thin wire. There are also some safety reasons if the wire snaps and you have pieces of wire floating, etc. So yeah, it's just too difficult to handle. That was a good compromise.
The question is not about the technology itself. It's about your role, let's say. So you're an advanced manufacturing engineer. How did you get there? I mean, like I'm in my master's. I just want to know because it sounds cool.
Yeah. So we have different engineering disciplines at ESA, materials, structures, propulsion, electrical engineering, etc., which provides advice and support to the big mission. When you make a spacecraft, you need a lot of different engineering areas. So ESA needs materials engineers. You have to select the materials, make sure that they are fit for purpose for space, etc. And my journey started in academic research in metallurgy. I worked in a research center after my PhD, and then I went to industry in aeronautics. And in people with aeronautic experience in materials are well appreciated in space because you work with similar materials, lightweight, strong materials, and you also have a high emphasis on reliability. I was working on airplane engines before ESA. If you fly an airplane, you don't want it to break during the mission. It's exactly the same in space. So this sort of background is good. Advice I would try to give is, yes, try to get some work experiences, internships, young graduates, etc., which gets you close to the type of problems we solve in space. I did that in aeronautics. You can do that in space. And then it gives you better chances of being attractive to recruitment in space companies or space agencies.
Thank you.
I had a question about support materials, but I think you already answered that about with different metal there. So my next question is, what do you think would be the next step to improve the resolution and reduce the need for machining? Like, would there be some correction process on top of the additive process, or you think there would be some hybrid systems creating the bulk shape with wire and then make powder just for an extra layers? What do you think would be the next step?
So there are different strategies. I would say the brute force strategy is you just machine with a tool. And as I said, NASA started working on hybrid systems which print and then machine. Another strategy is to refine the feedstock, so the material that the printer uses. So we talked about a thinner wire, powder with small particle size,